Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the radiation environment and its effects on the spacecrafts and the payloads. So, in the last session we discussed what is ionizing and non-ionizing radiation. So, as I said, that is non-ionizing radiation when it interacts with the material. So, there can be effect like the rise in the temperature, means whenever the electromagnetic whatever the radiation it interacts with the material, if it is non-ionizing, then it can impart energy in the form of heat energy. That means, the whatever the molecular vibration it may increase, there can be displacement of the atoms, but the energy of the radiation is not enough to make any of the to displace the electrons from its the outer orbits. So, these are the effects of the non-ionizing radiation. And when we discuss the ionizing radiation means it is having sufficient energy to dislodge the electron from the orbit of the that is the atom. So, then we discuss the ionizing radiation, we consider the energetic particles which is interacting with another target particle, and we define the terms like what is the linear energy transfer. So, we have seen that is the kinetic energy of the incoming the charged particle, it is imparted to the target particle, and the term we define, one is the linear energy transfer, where it is the energy transfer per unit length. Then we define a term that is the total ionizing dose, where it is the that energy transfer in terms of the what is the the mass, in terms of the mass. So, that is called the total ionization dose. And in order to discuss this effects, we defined the what is the stopping cross section, and we have seen that is how this term, especially the linear energy transfer, we can relate it to the stopping cross section. Then we defined the stopping range. So, we will continue with the discussion, and before I go to the next discussion, I like to mention that whenever we are doing deriving those equations, we considered that is the velocities of the charged particle, they are not relativistic, means we can apply the classical the Newtonian theory or classical mechanics. So, the kinetic energy we defined half m v square, and like that we derived the things. So, when it is possible to consider that that is this energy is it is the velocity is not relativistic, when the velocity is much lesser as compared to the velocity of light, means the energy of the particles are not very high at that time. We defined all those terms. Today we will consider the topic where we will use the relativistic the velocity or relativistic energy terms, and in that context we will just explain what is the difference between the classical and the relativistic the radiation energy. Then we will define or we will discuss a type of radiation which takes into which you have to consider when you are not considering the classical mechanics, that is you are considering the relativistic radiation energy. So, that is called the Bremsstrahlung radiation, and in this regard we will discuss what is X-rays, then gamma rays in terms of this Bremsstrahlung radiation, and then what is the effect of this the Bremsstrahlung radiation, that is X-rays, gamma rays, those effects, that is the photoelectric effect, then Compton effect and the pair production. So, these are the things we will discuss in this session. So, now let us discuss what is the radiation energy in terms of the classical mechanics and the relativistic based on the theory of relativity, that is Einstein's theory of relativity. So, when I say the relativistic energy, that is the total energy of an object moving at any speed, there is no constraint of the speed. So, the speeds can be closer to the speed of light. Okay. So, in classical physics, the energy of the moving object is mostly it is given by the kinetic energy. This is the formula, E is equal to half m v square, and this E is called the rest energy. E 0 is equal to m c square, where c is the velocity of light. So, for protons, this is about 939. You can calculate putting the mass of the proton and the velocity of light, you will and then convert it into electron volt, you will get 939 mega electron volt, and for electrons it will be 511 kilo electron volt. So, why this difference? Because here because the mass of the proton is much higher than the mass of the electron. So, whatever we wrote that, but you see the energy can be even in giga electron volts or even higher. So, that means this formula is no longer valid. So, when the velocity is very high, it is comparable to the velocity of the light, then you cannot use this equation E 0 is equal to m c square. So, there is a relativistic energy formula which is given by this formula. So, what is this term? So, this is the gamma is given by 1 by square root of 1 b square by c square, where is b is the velocity of the charged particle and c is that velocity of light. Now, when the object is at rest, so its velocity is 0, so then the energy reduces to the rest energy, that is why it is called the rest energy is equal to m c square. But when the v approaches the velocity of light, then the gamma becomes very large, in fact it is infinite. So, the total energy it can increase without bound. So, this is called when I wrote this E is equal to gamma m c square, then this is the total energy. So, you can write the kinetic energy at relativistic speed, that is kinetic energy is equal to E minus E 0, where E 0 is the that is the rest energy. So, then you can write using this this E and E 0. So, this is the equation. So, why it is of concern to us? Because you know there are very high energetic particles which are the giga electron volts, and so these are found you can found it in the solar energy particle bands or the galactic cosmic rays. So, we need to consider whatever we considered the earlier the session, where we considered these velocity which are much lesser than the velocity of light. So, that can only happen when the energy is low, that is it can be few kilo electron volt, but when it is going hundreds of electron volt or even in the mega or the giga electron volt, we need to consider this relativistic approach. So, at relativistic velocities, the charged particles may suffer greater energy loss when subjected to electrical forces in the vicinity of the atomic electron or the nucleus. So, we will discuss more in the subsequent slides. So, now we will define this radiation, that is Bremsstrahlung radiation. So, this Bremsstrahlung it is a German word which means the breaking radiation. So, it is a type of electromagnetic radiation produced when a charged particle, typically an electron, is deaccelerated or deflected by the electric field of an nucleus or another charged particle. So, you just consider this. So, few electrons they are approaching that is an atom, and there will be this all this electron, then there will be the electron as per the the atomic number of the there will be it can be more. So, like that. So, what will happen, this negative charges it will repel the electrons, but the nucleus which consists of the proton and neutrons it will attract this charges, and when it is doing that, so then the electron gets deflected. Now, when it is getting deflected, it gets deaccelerated, means its energy is reduced. So, that reduced energy it is it is emitted in the form of some radiation or in the terms of the photon. So, that is called the Bremsstrahlung radiation. So, at relativistic velocities, the charged particles suffer greater energy loss when subjected to an electrical forces in the vicinity of atomic electrons or the nucleus. So, atomic electrons means it will get the reflected, it will get repelled, or it will get attracted by the nucleus. So, as a result of these things it loses its energy. So, this incoming particle it has to lose the additional kinetic energy in the form of the energetic photons. So, that is called the Bremsstrahlung radiation. So, why it is needed that? Because the total energy, that is the conservation of energy or the momentum, and the momentum it has to be conserved. So, because of this it has to, when it is getting deaccelerated, or or it is acquiring some additional kinetic energy, it has to be it has to come in some other form. So, here you are getting radiation in the form of that is the photons. So, that we are defining as the Bremsstrahlung radiation. So, here this is called the photon. So, in photon this we do not consider the mass, and the energy we write in terms of h and nu, where h is the Planck's constant and nu is the that is the frequency of the this is the photon. Okay. So, so here you see we are not considering any mass. So, because of the relativistic effects become significant for electrons at much lower energies, that we have seen that whenever we are getting a 939, that is the kilo electron volt for electrons, we are getting that is the rest energy, that is equal to 511 kilo electron volts. So, that is why this relativistic effects it is more significant for the electrons. So, that is why the Bremsstrahlung radiation is of most concern for electrons. So, these photons, this means whatever this is this radiations, these are also the energetic, and they can cause additional damage to the surrounding material, that now we will see. So, it can be X-rays, it can be gamma rays. So, this now the energy spectrum of the that is the Bremsstrahlung radiation is continuous. So, because the electron can lose varying amounts of energy in the interaction. So, the lost energy that is emitted as a photon, so it can be X-ray photon having continuous spectrum of X-rays. So, it can range from 0.1 kilo electron volt to 10 kilo electron volt, or it can be high energy when the energy is from 10 kilo electron volt to 100 kilo electron volt, and sometimes it can be several hundreds of kilo electron volt, and then that will be the gamma rays. So, this intensity depends on the energy of the electrons and the atomic number of the target material. So, what is that intensity of this that is the Bremsstrahlung radiation? It depends on the what is the energy of the electrons and the what is the atomic number of the target material. So, when it is it will be more intense for the materials which have higher atomic numbers. When this Bremsstrahlung radiation or any energetic photons are incident upon matter, it too can interact with the target material and alter the material properties. That we will see. There will be some effects. What are those effects when this radiation it interacts with the particle? We will define those in the subsequent slide. So, sometimes when electrons have very high kinetic energies in the range of mega electron volt, the Bremsstrahlung photons which they emit, it can reach the energies in the gamma ray range. So, gamma range means when it is more than 100 kilo electron volt to mega electron volt, or in it can be more. So, we will just see what is the the X-rays and the gamma rays photons, what are their properties. So, because of the photons are unaffected by the electrostatic forces, because already they have they come out of that nuclei, or those the forces of the atom where it is produced. So, they will move in straight lines, that all until they undergo an interaction with the target material. So, it is that after this photons are created, which we defined as this Bremsstrahlung radiation in the form of X rays or gamma rays. So, they move in a straight line and then until they are interacting with the target material. So, in these cases the beam of photons, it can be X rays or gamma rays, they will have a probability for an interaction which is proportional to the area of the beam blocked by the target atoms divided by the total beam area. We will write it in mathematical form in the next slide. So, here we define the total cross section, that is sigma total. Previously we defined sigma stop when we are considering the the lower energy, and we are defining the linear energy transfer or the TID, that is the total electron dose. So, that sigma total it to be the effective target area of the nucleus, and this should not be confused with the actual size of the nucleus or even a sharply defined area. What it is actually, it is the if the photon and the nucleus are within a radius defined by. So, this is basically a the radius which is defined by the photon and the the nucleus. So, this is the boundary which we are defining as the sigma TOT or sigma total, and in that case they will, if they are within this radius, then they will on average they will interact. So, while the term cross section is applied to sigma stop, here also we are using the cross section, but they are having different they are different quantities, we will see it. So, so the unit of this sigma stop which we defined in the last class, these are energy into area, okay. And while the units of the sigma total, this is area. So, this is the difference between the sigma stop and the sigma total. Now, let us see what is the relation between the sigma total and the loss of photons in any material. So, it is defined by this. So, it is minus dN by n. So, this is the loss, that is why we are writing minus dN by n, and then what is dN? dN I can write in terms of n a into dx. So, dx is the linear distance, similar which we considered in the last class, and when you multiply by the sigma total, okay, and then this is what is the A is the total beam area, and in the beam area the total number of that photon line is n. So, then I can write this expression as, so this A and this A will cut, and I can write this n sigma total into dx. So, what is n here? N is the number of incoming rays, dN is the number of interactions, and what is that is the the number of interacting the photon lines, and n per meter cube, this is the target number density, and a meter square is the area of the target which is struck by the beam, and dx is the target thickness. So, I can write the intensity of the beam. So, now if you solve this, if you integrate both sides, then you can write that n x is equal to n into exponential this expression. So, what does it mean? That the intensity of the beam that will decrease exponentially, and this is different from whatever we discussed in the last class. So, there we have seen that the protons they move in a straight line, and the electrons they are getting bounced back or they are getting they scattered, but here it will, and we defined there a range where this this incoming charged particle will lose its energy, but in this case it needs x to be infinite to become the this intensity of the beam to become 0. So, now if we want to modify that expression by writing this absorber thickness in gram per centimeter square. So, we can write this expression in this way, where we are defining a new term, this is mu m. So, mu m is the absorption coefficient, which is defined by mu m is equal to n into sigma total by rho, and this we can write this in terms of the Avogadro number, and that is the atomic weight. In terms of atomic weight, we can write here again rho is the it is gram per centimeter cube, being the mass density of the target. Okay. So, if there is a composite material, so we can find this value of this mu m, which is the absorption coefficient, by this expression. So, it is basically summation of that is, so same expression we are writing it for but here we are introducing a term alpha I, where for alpha I is the relative abundance of the ith element. So, this is basically the ratio of the the electrons which is interacting by the total number of the electrons. So, this process of photon interactions with the target material is responsible for the absorption of the photon. So, what we are meaning here, that whatever we are considering those the photons generated because of the interaction of a charged particle moving at the relativistic velocities or having the relativistic energies. So, this the Bremsstrahlung that radiation which is interacts with the target material. So, there can be the effect like the photoelectric effect, then it can be the Compton effect, or it can be the pair production. We will see each of the thing one by one. So, and the total cross section, the sigma total, it will be the sum of the cross section for each of these three processes. So, now let us see what is photoelectric effect, that we know already what is photoelectric effect. So, it is the emission of electrons from a target material when the photons interact with the atom and the photon's kinetic energy is absorbed by the atomic electron, which is then ejected. So, each photon it carries the energy proportional to its frequency, which I already told in the earlier slide, where h is the Planck's constant and this is the value of the Planck constant. So, this is 10 to the power minus 34. So, it is joule per hertz and f is the frequency. So, electrons are ejected only if the photon energy exceeds the work function of the target material. So, then only you will have the photoelectric effect, that is the ejection of an electron. So, basically it means that this photon energy should be greater than, it has to be greater than the work function phi. So, then you can write the kinetic energy of the ejected electrons as Hf minus phi. So, this is the process shown here. So, the photons are coming and then because of that, so the particle which has energy Hf minus phi, so because of the work function, this kinetic energy it will decrease by Hf minus phi, and then these electrons are ejected. So, this is called the photoelectric effect. So, next let us see what is the Compton effect. So, it occurs when the photon is scattered off its original course of travel by an electron. So, when this happens, we call it the Compton effect, and by this effect there is an increase in wavelength. Increase in wavelength means it is the decrease in energy, or increase in wavelength means decrease in frequency. So, h nu or h into frequency. So, that is why it will lose the energy, or it will of the X-rays or the gamma rays when they are scattered by electrons. So, this Compton scattering, it dominates in the frequency range from 0.5 to 5 mega electron volt. We will see it in the some of some empirical curves. So, it applies, this Compton effect applies mainly to the gamma rays. So, the incident photon is coming. So, because of the the scattered electrons, so we are having a scattered photon. So, this is called the Compton effect. Then pair production. What is pair production? So, pair production is a phenomena where the high energy photon, means here we are considering the gamma ray, it transforms into a particle or antiparticle pair. So, particle and antiparticle pair means it is an electron and a positron, both are having the same mass, but one is electron is having a negative charge, whereas positron will have a positive charge. Okay. So, when it happens where it passes near a nucleus. So, pair production occurs when an electron and a positron are created from the photon. So, this pair production it must take place in the vicinity of the nucleus, because otherwise the energy and the momentum cannot be conserved. And it can be shown that this pair production cannot take place below this value. So, if you put me and see the velocity of light and the mass of electron, then you can see this is the figure 1.022 mega electron volt. So, making it concern only for higher energy gamma rays. So, this is the pair production. So, you are having this is the positron and this is the electron. So, electron positron pair. Okay. Now, let us see this is the 3 by the. So, this is the absorption coefficient given in centimeters per g, whatever we have seen, there is the mu, and this is the photon energy in mega electron volts. So, you can see here the photoelectric effect is it is mostly the prevalent where the energy is lower than 0.5. So, this is the reason. So, up to here you can see 0.5 to lower than 0.5s. Okay. And then, so this is you are getting this is the photoelectric. So, the next one is the Compton scattering. So, it is from 0.5 to 5 mega electron volt. So, this is basically this one. So, this is your Compton. And then you are having the photons having energy less than this one, which already we have discussed. So, this is this part. So, this is your pair production. And this is if you add all these 3, then you will get the total, this is the total effect. So, now we need to see that if I write this already we have written this, that is that is the photon for how it is the number is decreasing. So, it highlights one of the difference between the charged particles and the photons. So, charged particles, this exponential terms was not there if you compare it. So, charged particles will be stopped by a finite amount of shielding that we have seen. For each of the material there is a finite the range. Okay. So, it will basically the charged particle will be stopped while the photons follow an exponential decay. So, as such you can define the finite range for the charged particles. So, for the finite amount of energy, finite amount of shielding will always stop the charged particles, though sometimes this thickness required it may be impractical. So, this is the thing already we discussed. But if you see the case of the photons, the photons a given amount of shielding will reduce the flux, but will not stop. So, it will not stop the particles. So, the photons can, what we are discussing, it will penetrate to a depth where it will reduce. So, as for example, it will decrease by 1 by E when if you put your that x value is equal to E. So, you just see here. So, this term when is equal to 1, this one is equal to 1. So, it is given by 1 by sigma t total at whenever I am putting this value is equal to 1, then it is decreasing by 1 by this term. So, here the many photons will be absorbed before reaching this depth, but there will be some penetration, it is significantly further. So, that is why this is the difference it comes. So, you can see from here it will not this stop. So, that is why here we need to consider the effect of this type of radiation on the spacecraft will be different than as compared to the where the radiation particles which are having lower energy. We will discuss this in the subsequent classes. and thank you very much.